Hello, this is Mrs. Johnson. This is MAT221, Calculus 1. This is section 5.2, and we're talking about the definite integral. Now, what do we notice here? We notice that the integral from a to c, which is from this point here to this point here, is equal to the integral from a to b added to the integral from b to c. Notice that when the upper bound of one integration or definite integral matches the lower bound of another definite integral, we can simply kind of add these two integrals together and go from a lower bound of a to an upper bound of c. And we'll notice some other properties too. So this thing called the definite integral, the integral from a to b of a function, is considered the net area. Everything that we see above the x-axis we think of as a positive quantity and will be a positive quantity because the antiderivative curve should be rising on those intervals. And everything that's below the x-axis of a derivative curve should give us a negative quantity because that is where the antiderivative is decreasing. So let's look at this particular picture and look at these as areas and our knowledge of geometry here. See if we can use our knowledge of geometry to evaluate the definite integral when the figure is a known geometric shape like these triangles. So this is the line y equals x minus 1. So you can see it right there, that blue line. And if I wanted to know the definite integral from 0 to 3, I could figure out this region area, and this is the area of a triangle, and the area of a triangle is equal to 1/2 the base times the height, and in this case the base goes from 1 to 3, so that's 2 units, and the height is 2 units. You can see it goes up to a y value from 0 to 2, so 1/2 of 2 times 2. The area of area 1 is equal to 4 units. And we know the area here, area 2, would be 1/2 base times height again. That's another little mini triangle. And the base of the triangle is 1 unit, and the height is also 1 unit. So 1/2 base times height would be 1/2. But we know that area A2, that quantity, that integral, will be negative, and A1 will be positive. So if I wanted to know the integral from 0 to 3, it would be area 1 minus area 2, which in this case is 2 minus 1/2, which is equal to 3/2. I noticed up here I have a typo up here. This should be 1/2 of 2 times 2 would be 1/2 of 4, which would be 2. And I have it right over here, but I have it wrong up there. I just noticed that. So our integral would be 2 minus 1/2, or 1.5, or 3/2. So we easily can calculate here that the integral from 0 to 3 would equal 1.5. Now what about this example? This one I'm given a cubic function, which is not so easy anymore. Now I don't have geometric shapes that I can easily find the area of. So here the graph's not a geometric shape, so we must have to use other methods here to determine the area. So we can use the calculator or Mathematica here to find the value of the integral. And we could also break it up into pieces too. We could find out all these different pieces here. So I'm going to show you how to do this one on Mathematica also. But for right now, let's just do some analysis as if we were just not knowing what the area was. We know that the integral from 0 to 3 of this function, x cubed minus 6x, is going to be whatever this area A2 is, which we know will be a negative quantity, plus the area A1, which we know will be a positive quantity. We know that this point right here will be a critical point of the antiderivative. We know that it will be a local minimum because the derivative will be negative, then 0, then positive. So we know that will locate a local minimum. So the curve, the antiderivative curve, will fall this amount, A2, and then rise this amount. So looks like we should get a negative value overall because the area below the x-axis and the area above the x-axis definitely do not equal each other. And it looks like there's more area below than there is above. So the integral from 0 to 3 of this function is equal to area 1 minus area 2, which in this case ends up being 6.75. So let me stop the video for a second and I'll get back into Mathematica and show you how we can do this in Mathematica. All right, so what I did here in Mathematica is I again went into Mathematica and I said, okay, Mathematica, what is the integral from 0 to 3 of x cubed minus 6x dx? Now, in this particular case, I have to make sure that I'm going to take the antiderivative of that whole thing. So I get, okay, 27/4. What's that numerical value? It is 6.75. Now, there's a couple other ways we can also interpret this. Again, Mathematica is such a great tool for us to help us with a lot of these ideas. What I'm going to do is I'm going to plot this curve, and I'm just going to grab it here so I can copy and paste it into here. I'm going to just look at it from, let's go from like negative 0.5 to 3.5. So we're looking at it a little bit. There we go. It looks something like that. You could tell that's what the curve looked like from my PowerPoint, right? So we can definitely see that the area below the x-axis and the area above the axis when we're stopping at 3 here, we can even do that. Change this so that we're only looking from 0 to 3, so we look even better here. So you can see that the curve area below is a lot bigger than the area above. And if we wanted to find this exact value, remember Mathematica can find that too. We could ask Mathematica to actually solve this equation that I had there. Let's solve that. Where does that equal 0 for x? And it gives me 3 values at 0, at negative radical 6, which was over here somewhere in the negative domain, and then right here at positive radical 6. And if I took this here and I said, okay, got a new notebook there, which I didn't want to do. So if I say, what is the numerical value of radical 6? Okay, so this is right here is 2.44949. So that 0 right there is a pretty crazy, right? It's a radical 6 number. So what I could do here too is I could say, okay, Mathematica, what is the integral from a lower bound of 0 to an upper bound of radical 6, or that value that we just found, which was radical 6. Oops, that's not what I want either. Sorry. I want this equation up here. I want the actual function. This function right here. I'm going to just copy it. Definitely like to put it in here. Let's see if we can get it in there correctly. All right, so what do we know? We know that the integral from 0 to that point of intersection, which was underneath the curve here, gave us a -9 value. And then what I'm going to do is I say, okay, what is the integral from radical 6, which is that point that we wanted to 3 of that same expression. See if I can grab it again. I didn't have it in my copy post here, so I'm just copying and pasting it in here. And we get 9/4 So we say, okay, what is the value of -9 plus 9/4? And what is that value? The numerical value is -6.75. So you can see the power here of Mathematica. If we wanted to know, okay, how far did the antiderivative go down? That antiderivative from 0 to 2 to radical 6, so from 0 to radical 6, the amount of change in the antiderivative, or how far did it go down? It went down 9 units. And then from radical 6 to 3, it rose 9/4, which is 2 1/4, 2.25. So then overall, moving down 9 units, up 2.25 units. Overall, it went down in the interval from 0 to 3. It went down 6.75 units. So again, I love to show the power of Mathematica and how it can help us to calculate these values that we're studying in calculus. All right, so let's try another one. Let's interpret the definite integral from 0 to radical 2 pi of sine of x squared dx in terms of areas. So if I were to graph this, and I can do it easily in Mathematica now, I could say, okay, region A is this region from 0 to whatever that value, that 0 is of this function that's given to me next to the integration symbol, which again, remember, this is a derivative of something. And this area up here would be area A, and this area down here would be area B. So if we were just going to interpret in terms of area, we would say the integral from 0 to radical 2 pi of sine of x squared dx is going to be area A minus area B. And the integral looks to be positive from A to the very end over here at radical 2 pi. Because area A looks, which is the positive integral, seems much larger than area B, which is the negative integral. Now, let's actually go to Mathematica and figure out what are these values and how much is A, how much is B, and how much is the overall integral. These definitely would not be done by hand here. We're using the power of our technology to calculate these values. All right, so here in Mathematica, let's have Mathematica figure out our values here. We want to know from 0 to radical 2 pi. Oops, I have 2 pi's there. And my expression was sine, actually I put it in parentheses, sine of x squared. And it was dx. Actually, I should put these in brackets to make sure that it's going to do this. Oh, I have something quite crazy here. So you'll notice that I get something quite crazy here with my Mathematica, but as usual, let me go back up here, and we could always ask Mathematica to give me the numerical value of this, and of course it'll give the numerical value of this craziness that is, I don't know what that is, right? But it will always give us a numerical value. Let's also plot this. Let's put this, see if we can plot this function. Again, I'm just going to grab this function and I'm just going to copy and paste it in here. And we want it to go from 0 to radical 2 pi. And there's the curve that we saw in the PowerPoint. You can see there's the curve. Now, if we wanted to know how much is area A and how much was area B, we would have to find that 0 of this function. And again, Mathematica can find that by using the solve command. where is this function